For decades, some of the most powerful quantum experiments in the world have been locked inside massive laboratory setups, filled with lasers, mirrors, vacuum chambers, and delicate optics. But that's starting to change. Researchers are now bringing quantum experiments down to the chip level. At UC Santa Barbara, scientists are working on a breakthrough that could make quantum technology portable. By combining cold atom physics with integrated photonics, they're shrinking systems that once filled entire rooms into compact, durable chips. "We're at the tipping point," says Daniel Blumenthal, professor of electrical and computer engineering. So what makes this so important? It all starts with cold atoms. When atoms are cooled to temperatures below 1 millikelvin, their motion nearly stops and quantum effects take over. In this state, atoms become incredibly sensitive to tiny forces, electromagnetic signals, and even subtle changes in gravity. That makes them perfect for ultra-precise timekeeping, navigation, sensing, and even quantum computing. The problem is scale. Traditionally, trapping and cooling atoms requires bulky free space optics, lasers guided by lenses, mirrors, and modulators, combined with magnetic fields inside a vacuum chamber. These systems are powerful but fragile and impossible to deploy outside the lab. The challenge has been figuring out how to replicate all of that functionality on a chip. That's where integrated photonics comes in. In a recent Optica quantum review, Blumenthal and his team highlight a major milestone, a photonic integrated 3D magneto-optical trap, or PICMOT. Built on a low-loss silicon nitride platform, this system generates, routes, expands, and controls all the laser beams needed to trap and cool atoms, all on a single chip. Instead of free space optics, light is delivered through waveguides from an optical fiber thinner than a human hair. That light is then directed to grating emitters that produce wide, precisely aligned beams. These beams intersect inside a tiny vacuum cell, trapping up to 1 million atoms and cooling them to just 250 microkelvin. For the first time, cold atoms were created using integrated photonics. And the implications are huge. Chip-scale quantum devices could enable portable atomic clocks, ultra-sensitive gravity sensors, and deployable quantum instruments for Earth observation, space missions, and fundamental physics experiments. They could help measure volcanic activity, track glacier movement, or detect subtle changes in sea level by sensing gravity itself. Beyond applications, this technology could transform research. By eliminating complex optical setups, scientists can spend less time fine-tuning equipment and more time making discoveries, opening the door for a new generation of accessible quantum experiments. Quantum technology is no longer confined to the lab, it's being trapped on a chip.